Okay, so now we're live. I didn't realize that I didn't realize that actually YouTube changed one thing now, and so when you connect the streaming software, it actually starts a live stream right away, and it starts a live. That's why you kind of saw a hiccup. I think if you connect it, if you I was just went live for a second and then disconnected, and it was a hiccup from I hadn't realized. Usually, I connect the software, the streaming software, and then I still can hit the actual end stream button on the YouTube Studio, and then it goes live. Just to check quality and stuff like that. But it seemed like it went live right away. So anyway, we are going to be discussing today in the Discord with other people about the original VQE paper. So I'll share it in the chat. Let me see. Uh, where can I find these? We had it in the Paper Club channel pinned in there. So we read basically this was actually supposed to be for last week already, but I didn't make it because of a bunch of other things that I had to do, and then we kind of ended up putting it off. And so we're going to we read the original VQA paper. Let's see. I'll put it in the chat. So we are discussing this paper. So I'm gonna have to give it some minutes still, okay? So it's like, what time is it now? It's 10 to 5, so it's a bit early. Let me see if I can open the paper myself. Yeah, it's a variational eigenvalue solver on a quantum processor, and I think that's a paper from the Alan Asparuh Kuzik group, and it's from 2013. I gotta. Whoa, whoa, whoa! What happened? Sorry, I just zoomed in too much. I gotta fix my streaming settings because I'm definitely not like when I'm streaming or I'm recording using OBS. My whole I think it just takes too much CPU, and then I can't scroll through PDFs comfortably. So that is definitely a big problem. I'm gonna see if there's anyone else joining. If not, I'll go get a coffee actually. So stay tuned. We'll be back in like probably 10 minutes or 5 minutes or 10 minutes or so. So I'm back, but I'm still waiting for the other guys to join the voice discussion. Um, who's watching, by the way? Just see a couple people. Say hi in the chat if you want, just so I know who's watching. Uh, yeah, it's been a while since we did the weekly quantum Discord last time. As I said, I had to travel for personal reasons, and then it basically didn't make it to organize these. But we're gonna keep trying to keep it. Oh, I'm in general now. I see. Sorry. Now Amir can hear me probably now. I was in the general voice channel.
Ah, well, I mean that would have been fine too.
Yeah, but actually, yeah. I mean, I just saw your avatar floating over there. It's like, well, good. I don't know. Do you know if anyone else is gonna join or?
No, it may just be us two.
Okay.
Um, yeah,
I mean, I don't know. I don't know about you. You said like did you refresh the paper because you already had read it for last week, right?
yeah. I didn't read it again, but I had already taken notes, so um, yeah, so it's easy to like jump back in for me.
Cool. Like
Yeah.
I thought so. I hadn't read the paper before, despite all the stuff
Mhm.
that I've done in VQE, and I thought it was pretty dope that actually the paper, like, I was really surprised when I started reading and I realized that, like, they actually built an actual, like, device.
Yeah,
Like, I was expecting, like, hey, that's the algorithm and it will work in theory and here's the code, but then I realized that that's from 2013, right? Like, and
yeah.
2013 there was definitely no IPMQ or anything, right? Like, there's nothing publicly available,
Oh,
to test these ideas on, I guess.
yeah. What was I'm looking at the picture of this. How many qubits did this have? Did this have
It just had 2 qubits, I think,
oh,
because
just two?
yeah, because they said they could. They said that then with the device they could then study like 2 by 2 Hamiltonians, or was it 4 qubits? I think it was just 2 qubits. Let me see if I can.
Yeah, I'm trying to make sense out of the diagram,
Yeah, it's just
figure
I think it's just
2A.
it's 2 qubits. Like in the figure two, the A diagram, like it's got the initial state 0 0 in
Zero, zero, yep, and then four readouts.
in CAT exactly, and then four readouts. Yeah, I found.
Actually, that's
Go ahead.
four readouts.
Why four readouts? I guess that's because this is photon counting what they're using, but I'm not. I didn't go too deep into the extra theory that they attach there as well. Um, so I don't know actually why there are four readouts. Is it for the 0 and 1 of each?
Yeah, I'm trying to make sense of the. Why do we do that? It could be based on their expectation. Are they doing? Well, no, they wouldn't be able to do two
No, no.
measurements anyway.
The expectation value. What they say, they make a reference to a paper from the year 2000 where they basically, well, it is explained that to calculate the expectation value of an observable, you just do repeated measurements and average the results. But I'm assuming that has to do with the fact that it's a photonic system, and it has to do with the way they measure was photon counting. I think what they're saying, and I don't know if this is like I remember from the course that I took on like the Future Learn platform, that the way photon counting works is like, I think you count the photons that arrive at a different interval of time. I think so. Like the ones that arrive first, like that's kind of a 1, and then if it arrives with delay, it's a 0 or something like this. So I don't know. Maybe it's something along these lines, but I didn't really dig too much deep into the technical details. But I found it funny. I found it funny that it was like it really seems like the actual algorithm is not like the point of the paper. It's more like, hey, here's a device that like can do this, right? and they actually they put more emphasis into the first thing is how to calculate the actual like the eigenvalue without really using QPE, right? The phase estimation, and then the variational part. But I mean, there's not even like the mention of there's just one sentence I think somewhere at the bottom of the paper where they say, yeah, and here's what you do, something like whatever gradient descent or whatever like optimization technique you want to use, and that's how you do it. Like, but it's really the emphasis on just the fact that you can break down a Hamiltonian into like a linear combination of Pauli operators, and then just do the expectation values of each part and add them up, and that's it. I don't know. I really liked it. I enjoyed a lot the fact that the paper felt really low key. It was not like, behold my new algorithm. It felt a bit more like, yeah, it just tinkered a bit with a couple of cables here and there, and it worked out. Yeah.
Yeah. I was reading below the figure. It says coincidence count rates from the detector D1 through 4 are passed to the CPU. So yeah, I think.
So if there's like a simultaneous hit, it's probably whatever, like a 1, and if there's no simultaneous hit, it's a 0 or something like this.
Yeah, I think so.
Okay. Cool.
Yeah, cool. Yeah, the what you mentioned about the the gradient descent in the appendix, they said they couldn't use gradient descent. They had to use Nelder-Mead.
Oh, really? I didn't read that part. Okay.
Yeah, due to the experimental conditions of their device. So, gradient descent failed, and I don't think they went into much more. Let me see where search for gradient descent. Gradient descent is not robust to noise, which makes the objective functions smooth under experimental conditions. So, yeah.
Maybe because of, but I mean, it's used now.
I think it's used now.
It's used now, but because maybe the noise reduction is, or because basically the QB qualities is higher now than like 7 years ago.
Yeah.
I guess.
Yeah, they weren't able to converge to the ground state when they did it initially, but simplex space. I'm not familiar with Nelder-Mead. I mean, I've heard of it for optimization. I just don't know how it actually works.
Okay. No, me neither. I mean, I'm actually not familiar with almost any optimization stuff. I definitely want to dive into these as well. Together with VQE and variational stuff, I think. But it's quite amazing that from just like, this paper, like so much actually emerged now that is used in terms of all the variational stuff. Because have you did you read the part of the paper where they say something about excited states, like? Because I think I wanted to come back to that. I never had the time to, because that they have like they've released I don't know when they released another version of VQE, or no, it's not a version, but it's like another I forgot how the algorithm is called, but like it's inspired by VQE, and it's to find any eigenvalue. So not just the one, like the lowest one, but like any, which is basically. You do VQE, you do a run of VQE to find the lowest energy, and then you keep iterating and you do new iterations of VQE, but your cost function has an additional component, which is the overlap between the eigenvalue that you're going to find, sorry, the eigenvector that you're finding versus the one you found previously, and you want to minimize that overlap. This means that the next eigenvector you find, or eigenstate you find, is orthogonal to the previous one, and so this means that it's kind of the next eigenstate, right? And
Oh,
so,
that's cool.
and
Yeah.
then you iteratively kind of build up the whole spectrum, and then you can find higher levels. And it's funny because they really used a really similar figure, like the figure one, with the quantum modules and all this kind of stuff. But for me, it was nice to see the difference of the style in the paper, right? Where, because you see the figure one and you kind of see, okay, there's a box that says quantum state preparation, and then it splits into different boxes that, it says quantum module one, quantum module two, and those are the subcomponents of the Hamiltonian, I guess.
Mhm.
And it really feels like, this is kind of so much tied to the fact that they probably that's how they envisioned implementing it, like from a physical hardware perspective, rather than kind of having a more programmatic approach. I don't know, because if someone would write this paper now, it would be more like, this is the Qiski code, and there you go, right? And I don't know, I found it interesting. Yeah, but you said you took some notes. Like, what part did you focus on for the notes?
Oh, well, I guess with most of my notes, they're just, I try to read through the paper, um, and just pull out the parts that I find specifically, here. I'll post this to the chat so that
Okay,
if
okay,
it's of
cool.
value to people,
Yeah.
yeah, it's easy enough to do. Let me go ahead and post that. I also usually write some questions that I'm hoping maybe you and I can discuss as well.
Oh yeah, definitely.
Yeah, because that's the good point about these. The paper club is we can discuss things, and
Exactly.
if I were just reading the paper on my own, then
Yeah. Yeah.
I might, I'd be at the yeah. So there, I posted it.
Oh yeah. So now, cool.
Yeah, are you able to see that?
Let me open Rome Research. Do you actually have to have an account to see them?
No, it should be.
It should be
It
public,
should
right?
just be. Yeah. Yeah.
It's loading still.
Okay. Yeah, it's weird. It loads and almost seems like you would need to log in, but then I think it detects that the page is public, so then
Okay.
it
No, there's this icon with this that looks like an engine or like a turbine or something. Okay. Yeah. Okay. Now I'm in. Yeah.
yeah. Okay. Cool. Yeah. So I go through the paper in each section and write notes that pull it out, and I think for me these notes are just a way that if I'm searching through all of my notes and this page comes up with a hit, like if I just search for expectation, this might come up, and then I would be able to go back to the section if I wanted to read more.
Nice.
Again. But each person has their own style for notes.
Yeah. Definitely.
Yeah, I really like this paper too. Just the style, as you're saying, it's I like how you said it's almost modest in how they wrote it.
Yeah.
But yet, yeah, it's just like here they introduce this device. They introduce a way of splitting. I like that they looked at even parallel, having many of these devices going, and you could potentially just split your Hamiltonian into terms and then calculate each of those in parallel.
Yeah, exactly. I found this really interesting. But was there any specific part? Because, for example, from my perspective, like it's also a matter of taste, I guess. I just didn't dig. I just was. It was, I guess, a matter of time and then laziness, which is bad. But I didn't put too much attention into the actual examples. Did you do that, or you also just skim through them because they have then in figure 3 and figure 4, I mean, they talk about what's that?
Oh yeah,
they actually have some examples with with this atomic separation and all that stuff. I didn't really follow that. I just read through and that's it. But I don't think I really, because they talk also about the this cluster operator, and that felt like it needed just too much digging, and I just I don't know, I didn't dive into this.
Yeah, so from the Kiskit Summer School, the final project was on estimating the ground state of the lithium hydride
Mm-hmm.
molecule. And I think that's just slightly more complex than the one they use in the paper.
Okay.
Again, classically, easily, you can calculate that easily. But yeah, so only because I've done that final project did these graphs make a little more sense to me.
Okay.
And were kind of interesting just because of the results they got, and compared to the theoretical, the I guess figure 4, this graph where it's like it dips and then comes back up. That's a
Mm.
common one,
Okay.
because like the lowest point there is obviously your ground state, um, and yeah, and then as you wish I don't know where my other graph is, but when they were explaining this stuff to us, to the right of that is where the bonds dissociate. So the separation between the atoms
Mm-hmm.
gets so large that then I guess the molecule won't
Okay.
hold together. Yeah. So and then when the interatomic distance is too short, so that huge wall right before the lowest point,
Mm.
I guess it requires too much, too much energy to keep those atoms at that distance
Okay.
from each other.
Uh-huh.
Yeah. So anyway, I'm explaining. Maybe you already know all this. I'm new to
No, no,
chemistry,
no.
so
I'm
quantum.
I'm new to chemistry. Yeah, I'm new to chemistry from that perspective as well. Other than like what you just do in high school and stuff. Like
Yeah,
I didn't do any chemistry after high school, so
yeah. One thing. Do you know is the chemistry we did in high school? I sometimes hear the term quantum chemistry, and I'm wondering, is quantum chemistry any different? Is that just chemistry, or is that a different? Like, would that be different than what we probably learned? Because we're probably similar in age, so
yeah,
for
maybe.
whatever we learned.
Yeah, I mean, maybe when people talk about quantum chemistry, they just refer to maybe like the study of like subatomic stuff, right? Where
Uh,
you observe the actual quantum behavior, I guess.
oh, yeah, so that makes more sense. So when we are talking about these, yeah, I forget what, yeah, because I feel like the chemistry I did was more about like solutions
Yeah, yeah,
and,
totally. That's
you know,
exactly.
yeah, so subatomic makes sense then. It would be for quantum chemistry.
Subatomic, or maybe because I guess it's a difference. There's a difference between quantum chemistry and using quantum computing to solve some chemistry problems, right? Like, because I'm assuming you do have like chemistry problems. Maybe if you go even the direction of like material design and or whatever else. Like I don't know at what point the two branches like touch, but there are problems that just because of their complexity could be solved with quantum computing, but they are not quantum chemistry problems, right? It's just a matter of I think that if you quantum chemistry as a discipline, if it exists at all, it's probably subatomic. That would be my guess.
Here's an interesting point about their experiment. It took them 158 hours.
Oh, really?
Yeah, so
I
they
didn't.
ran 100. Yeah, this was in the appendix.
Oh, I didn't
Um,
catch that.
yeah, so it took 158 hours with they found 79. Wait, with ground states found for 79 Hamiltonian. 100. Oh, so they did 100 measurements per ground state run.
Okay.
So per interatomic distance on like figure 4. Yeah, I guess all their blue dots. So
Mm-hmm.
there are 79 of those, and then they did 100 measurements per ground state run. So one thing I didn't do the calculations of was to try and figure out, like reverse engineer what clock cycle this quantum computer ran on. It would be interesting to know how fast this same experiment,
Could be
would
done
take on
now.
a new, done
Well,
now, like, and if our clock cycles are any different
yeah. I
now.
mean, we definitely can try that. I think that's a nice idea for like a one or two videos. I'll take note of
Try
it.
and reproduce.
Yeah, yeah. Just to try to reproduce the experiment and then see. I don't know if there's enough in there to be able to replicate this properly, but I think so.
Well,
I
so
mean,
they told us, yeah.
they
Go ahead.
tell what ansatz they use, right?
That's yeah. I mean, they say they use the UCC SD for their ansatz, or did they? Did they end up using that? Let me see.
I don't know. I was saying before you came, like I have to figure out what the right setup for OBS is, because as soon as I get the streaming software on, like I can't scroll PDFs almost. It just goes like
Oh no.
it's got such a delay, and I see the CPU usage of OBS is about, it's like about 11% right now, and I think it's just a matter of like tuning it a little bit down, and then. And it makes it super hard for me to search in the PDF, because like
Okay.
I easily scroll past or scroll past things, because I can't control this super easily. But
Yeah. So
you found it?
I think so. It's let's see. Yeah, it's under algorithm 2. So they bolded that. It's right on the same page that they're talking about the actual QPU. Then they start to talk about their ansatz.
The ansatz.
Yeah, it says where, so they set up this state psi e to the t minus t dagger, and then they're saying t is the cluster operator, which they
define in the appendix. Okay.
Yeah, the appendix. Yeah, so unitary coupled cluster theory. This is now, I think, referred to more commonly as UCCSD, which is unitary coupled cluster theory for single and double excitations.
Okay.
Yeah, so like when when you're in Qiskit and you want to figure, create an ansatz, that's one of the libraries you have available to you.
Okay.
So I would assume that that's the same thing as what they're saying here, but they don't mention the SD part. So I don't know if this is more general or not.
Okay. Yeah, but we could. Yeah, but I mean, could give it a try anyway. But that would be an interesting experiment to try and reproduce the same and see how much it would take now. I guess, I mean, it's not, if you're tinkering with a device like that, by yourself. I mean, it's and I guess this is a photonic setup, so maybe it would be the most fair would be to kind of use Xanadu or something like that.
Oh yeah, stick with yeah.
Because that's basically the same concept. And see a difference. Yeah, I didn't catch that with the timing, with the 180 hours you said.
158.
58. Yeah. Sorry. Okay. Cool. You said you had some questions.
Pretty significant, thinking about running experiments that long.
Yeah, definitely.
Yeah. Obviously, you could break that. You can still break that up because. But yeah, my patients, I would want to verify that things were working. This is my problem with any of the machine learning is. I'm kind of.
I know where you're going.
What?
I know where you're going. I think. Yeah.
One of my frustrations with any of is I hate the idea of wasted cycles. So the first thing I usually do, like it's funny, whenever you're using one of these machine learning packages, by default they kind of they won't have clip iterations early. So you can keep. I always like to look at like how fast things are converging, and once they slow down, I just I usually want to kill the process. So like rather than running like 1,000 iterations or epochs of something, I like to see as I go with a greedy approach, which may not be the best approach, but I like to see like what's the fastest. What are the fastest parameter? What are the parameters that give me the fastest convergence in the first 100 iterations? As opposed to and then once I find some of those good parameters, then I don't mind letting it run for a while. But a lot of the setups, like even in the final project, it wasn't set up that way. in the Jupyter notebooks. So like when I was watching some of my teammates go, they were just letting it run. There's just all these wasted cycles
Yeah.
during our experimentation phase. Yeah, that drives me mad.
So 100. So it's like, yeah, and it's like, what if something's just wrong, or yeah, like at some point
Yeah.
at what point do you decide to stop? Yeah, that's actually. Um, you said you had some questions. I'm curious which ones.
Yeah. So yeah, one of these is, I mean, I guess it was mostly around this ansatz, which I don't know. We could try and figure these out on our own, but maybe even one of them was just the way it was written. So it's mentioned. Let me see if I can find the location. It's mentioned that the coupled cluster ansatz, that there's no known classical solution. And it's kind of weird how they wrote it because, sorry, I'm just trying to find where that is. Yeah, there's currently no known efficient classical algorithm based on these ansatz states. And it's kind of weird because we know we can solve this, the molecule they chose classically. So then what I was trying to understand is, are they saying there's no known classical solution using the ansatz or for preparing them? So let me just give you it's on the same page as when the QPU figure 2. It's on the second paragraph. So it says,
So it's,
yeah, they're talking about using the unitary coupled cluster ansatz.
Yeah.
Normally taken to be the Hartree-Fock ground state. And then it says there's currently no known efficient classical algorithm based on these ansatz states.
Yeah, I found this. There's currently no efficient algorithm.
Yeah, they didn't make a lot of sense.
States. Okay. But isn't the Hartree-Fock thing like an algorithm as well? Like, isn't it like an actual algorithm to approximate the ground state?
I think so. Yeah.
And I think that's I think that's what they're saying, is that algorithm doesn't have an efficient classical solution. I think that's what they mean. And what they say is that the Hartree-Fock ground state, whatever algorithm, is using also the cluster thing as a reference state. So they also use it as an ansatz, and it's the only algorithm that is using it, and that it's known, but it's also not efficient. I think that's what they mean.
Okay. Okay, I didn't read that initially as so you're thinking they're saying there's no known efficient classical algorithm based on using the Hartree-Fock ground state.
Exactly.
Okay.
I think that because the Hartree, let me see if I just quickly check the Wikipedia entry for this. The Hartree-Fock method is a method of approximation for the determination of the wave function and the energy of a quantum many-body system in a stationary state. Let's see if there's something about the cluster.
Yeah, I'm searching for efficient Hartree-Fock.
Coupled cluster is a numerical technique used for describing many-body systems. Its most common use is as one of several post-Hartree-Fock ab initio quantum chemistry methods. As a post-Hartree-Fock ab initio.
So yeah, I think you use them together.
Yeah, it seems so. The coupled cluster is a numerical technique. Yeah, but I agree. It's written in a funny way. It's in a weird way where it's like T is the cluster operator, and then it's some reference state normally taken to be the Hartree-Fock ground state.
Yeah.
Okay. I guess what it means, the Hartree. So maybe what this means is that that this state is the Hartree-Fock ground state. It means it's the state you find with the Hartree-Fock method, right? And then that's when you use the coupled cluster method after that, like to that maybe makes more sense, because here in the Wikipedia it says it's a numerical technique used for describing a many-body system, and it's commonly used as a post-Hartree-Fock. So it's kind of, and now I would assume when they talk about the Hartree-Fock ground state, that's the outcome of the Hartree-Fock method. You get a ground state, or you get an approximation to the ground state, and then you use that. But as far as I understand, these algorithms are just not like that. They're not efficient.
Okay. You mean you probably the two of them together on a classical computer?
Yeah, exactly.
Okay. Yeah, and then for a quantum computer, we're still making use of them, and then I think we're encoding it to qubits. You know, encoding those Hamiltonians to qubits, and that's maybe where the benefit comes.
Yeah, I don't know what the relationship is between the cluster, so the coupled cluster and the actual ansatz, like, is, because I don't really know anything about the coupled cluster method. Like, it says it's a numerical method, but like, how can this inspire an ansatz? You know what I mean? Is it just just a mathematical mapping? Like, okay, yeah, because you have these metrics, like these gates, and you multiply them together, and you can turn that into a quantum circuit, and so that's the ansatz. Maybe that's the way that you map it. It's purely a mathematical equivalence, right? Like between the method and so you're translating the method into a set of operators, and then these operators just translate them into an actual circuit.
Yeah.
I tend to forget that a lot of this stuff just happens this way. I'm always thinking that we're in a world where like people's like, oh yeah, that makes total sense. We put these pieces together and it's more intuitive, but sometimes it's just not intuitive at all. You just take a method, you translate it into some sort of unitary operators, and then make a circuit out of it.
Yeah. And that's where I don't know if that's covered in this paper, but that's where the Jordan-Wigner transformation, like there are different ways to transform into qubit Hamiltonians. Yeah, let me see if they specify that.
So they say that's in the appendix in the beginning. It says the map from the fermionic algebra of the second quantized Hamiltonian to the distinguishable spin algebra of qubits is given by the Jordan-Wigner transformation.
Yeah.
Which, for our purposes, can be concisely written as... What's the fermionic algebra? Do you know that? I don't know if you lost the connection or the microphone. I can't hear you.
Oh, I was. I thought you were reading. Maybe.
No. Sorry. No. I was asking whether you know what the fermionic algebra is.
Oh well. So from the, again, very limited understanding, but from the final project, I'm reflecting back what you were already saying is like a lot of these steps are just getting the problem into a representation that works. Mm-hmm. So, we start with this Hartree-Fock, then we use it sounds like we're using this unitary coupled cluster approach to turn it into, like, to get an ansatz for that, I guess. Mm-hmm. And the naive question there, well, let's just pause there for a moment. So the naive question there is, if you can calculate the ground, like with Hartree-Fock, if you can approximate the ground state, mm-hmm. then I wonder, like, what are we actually doing? Because is it that you have this ground state and then now you're wanting to see the actual energy associated with that, the eigenvalue associated with that?
But what do you mean? What do you want to do with the combination of the Hartree-Fock method and the coupled cluster?
Well, no, I'm just saying even the fact that if Hartree-Fock is giving us back the approximated ground state, some part of me was thinking that VQE is about finding the eigenvalue and not the, because
So
you're giving it the
no,
ground state,
you're
the
so
eigenstate.
so so VQE is about VQE has two parts. That's how they describe it in the paper. The first part is figure out a way to create or to approximate the ground state, right? And then once you have an approximation of the ground state, break it down into different modules that basically apply each Pauli operator that are the separate components of the Hamiltonian, and then do the expectation value calculations, and then based on these give it to a classical optimizer so they tweak the parameters you've used to approximate the ground state so you can find a better approximation of the ground state. I don't know if that was clear, because I keep having to go back to this as well myself. Like what you're giving to what you're doing with a parametrized circuit is you're preparing a state that you think it's a good approximation of the ground state. What a lot of variation algorithms do is they just start somewhere randomly. They select like a random value for all the parameters, and they just start at somewhere random.
Yeah. I think I want to get a little more precise with this, because when we say, like when I parrot back, like if someone was asking what's VQE used for, well, I've said to find the ground state of molecules, but I think it's specifically the ground state energy.
Yeah.
Because we have the approximate. Yeah.
Exactly.
Okay. So because taking these expectation values is the point of calculating the eigenvalue of the eigenvector.
Exactly. And that eigenvalue is the energy.
Yeah. So coming back to Hartree-Fock, so we're getting this approximated ground state. Then we're using UCCSD, I think, to create like a good starting point to then converge on that ground state and then calculate the estimated energy from that.
Yeah.
And so, but the UCCSD, it doesn't give you something that's easily computed on using qubits, and that's where you need that additional transformation to map it to, in this case, polyspins. But there are even more approaches than just this Jordan-Wigner transformation. There's the what was that? That was I'm going to say Vazirani, but they're let me see. Let me go back to the summer school real quickly, because they mentioned this. It's a Bravi-Kitev approach.
Okay.
Yeah, because Jordan-Wigner, that transformation has been around since the 1920s.
Oh, okay.
Yeah, so then in 2000, Bravi and Kitev, Bravi, who works at IBM, same researcher, they were just better mappings from the fermionic to this qubit mapping. Yeah, and so I mean, think about like that's many levels deep. So you could probably use a bunch of different approaches to getting the fermionic Hamiltonian. So you already have some like experimentation there. Then you go from fermionic to then you have many approaches to finding your ansatz. And then you have many different approaches to converting to a qubit mapping. And then once you're at a qubit mapping, then you have many different classical optimization algorithms to choose from. So to your point, like stringing all these things together is, I think, some of the work of figuring out how to, make use of, that's like the tough work, is like figuring out all of those things together that you can then get something useful out.
Yeah, I mean, yes, the thing is, like, I feel almost like everything else that you do before you get to sort of the qubit the qubit representation. Isn't it like something you just do, like they've done this by choice in the paper, right? Because I think the core idea out of this is the concept of the variational. It's like the variational concept, right? Like you can just start like with a random ansatz. Oh, sorry, with an ansatz, but like with a random set of parameters, and then you just don't have all this work, right? You just you start with a random set of parameters, calculate the expectation value, feed it to the optimizer, correct the parameters, based on the gradient or whatever, and kind of go ahead. I mean, I guess that's kind of the core idea that everyone has been then reusing for other things. Like this whole story here with the with the hard tree fork process and method, and then all this kind of stuff like that you do before, so you get already a really good initial approximation of the ground state. It's just kind of like, I don't know, a choice, I feel.
Yeah. Although some of the approaches can reduce your actual number of qubits needed, so
yeah, definitely. I'm not saying they're not useful. I mean, not only that. I mean, you definitely will avoid probably, or you will have, the chances you end up like in the actual, the actual ground state are better, right? Because you have already done some pre-calculations. Because if you just randomly start somewhere, like then you have all this plateau problem, right?
Yeah.
Yeah.
Well, since you're talking about actual implementations, or like, well, not actual implementations, but something that's related to that was in the paper, and it was talking about how, because they relate that another approach to solving this problem is using quantum phase estimation.
Yeah.
And in the discussion section of this paper, they said that a QP circuit for a 4x4 Hamiltonian, 4x4 matrix, would require 12 CNOTs, and for VQE, the equivalent is only 1 CNOT. So, and that's the cool thing about VQE is you also are not using any auxiliary. I can't say that word right now. And I was up early to qubits. Yeah. So, it's cool that you're kind of making use of the full power of your noisy machine with this algorithm.
Yeah, exactly.
You're using every qubit for a necessary, purpose. Yeah. So.
Yeah. Because QPUE, it's just it's monstrous in comparison, right? Like if you think about all the controlled unitaries you have to have, and then you still have to run the inverse QFD, right? Yeah. Yep. But other than that, anything else that caught your attention?
Well, a question for you, because I know you've done, just with all of the experimentation, I really like that you're now reading the paper, but you've experimented a lot with VQE firsthand and with other algorithms like it.
Yeah.
Anything new dawn on you, or as you were reading through this paper, either from your own experimentation, I guess, was this paper more confirming your own experimentation with this process, or did you actually have any aha moments through?
I didn't. I think I didn't have any aha moment, or any special aha moment on this, like while reading this particular paper. Other than like, sort of the confirmation of, it's just this. Like it feels like, before I actually read this paper, when I was doing playing with other variational algorithms, they felt like they were being a bit oversold, and there's a lot of fanciness around the way they're explained, and I haven't really played a lot with many of them, right? Like I still have a long list of stuff that I wanna do there, but like the more I played with this stuff, I realized that like the core principle is really simple, and I was really happy that this paper really transmitted that simplicity, that it's like, yeah, that's it, just find a way to, programmatically fine tune or change the actual phases of the different qubits. Like I think that's the way they do with whatever. I don't remember the names. Like how they actually do the fine tuning of the parameters, but like just it's just like this. It's a simple concept. It's yeah, that's kind of was it was not an aha moment, but it was more of a confirmation. So I was happy. I was happy that this was really. It really felt like a Handball paper. Yeah.
Yeah. I wish more papers were written this way.
Yeah, exactly. I mean, now it's like what I like about this is that it really goes, like end to end, right? So it goes from like theory to actual practice, and so they actually have that physical device in there now, because you have already bigger machines, and you can just go and run the code on like IBM machines, for example. You will always probably lose some of that I don't know, enchanting point, like, or I don't know what's the right English word to use this, but like it's a bit of this. I don't know. I find these papers attractive, but now it's kind of more difficult. Another paper that I really liked, that it felt quite similar, but it's nothing to do with variational stuff. But it was the paper from the team from Rod. I forgot his name. His full name. I'm so bad at this. But it's a paper about a way to implement Grover's Oracle that can run on like NISQ machines, right? So that it's like the subdivided
His name,
phase.
Is that this company called BEIT, I think? Is that?
No. It's not a company. He's working at a university. I can't remember. I can't remember really the. I mean, he's the guy who did the FutureLearn course. Oh, it's called FutureLearn. It's a shame, because like these people definitely deserve more.
It's not Vanderspies Center, is it?
No. He works at the Keio University.
Okay.
Rod van Meter, I think his full name is. RDV. I think his Twitter handle is like RDV something. Anyway, the paper is really also it kind of has like a nice feeling as well. It's really humble in terms of like, we play with these, and we go all the way from like theory to practice. We play a little bit with these, and we see that you can actually get some interesting results out of that. I kind of like these papers, but it's a personal taste as well. Like when it's really dense with just a lot of math, and there's not even like sometimes the effort to translate things into circuits or something like this. But I can also understand like why some people also don't, it's not that, I don't know, I don't think it's probably fair to make it mandatory for people to go down, the level of drawing circuits and whatnot. Like if whatever you're trying to prove with your paper can be neatly explained mathematically, should also be fine. But it just makes it always easier to replicate. Yeah. But I didn't have any, going back to your question, I didn't have any like special aha moment. It was more like, I was happy to see the simplicity behind the whole concept. And to be honest, in general, while exploring variational stuff, I'm really at the very beginning, and actually, I did enjoy discovering, like, and playing a little bit with the whole Baron plateau thing, like about how actually initializing your ansatz with random parameters, it's just actually kicking you, it's killing you. It's not like you're gonna get stuck. You're not gonna be able to really find as you increase it's one of those things where it's funny, because people say, oh yeah, VQE and variational stuff is a great application for NISQ machines, right? And at the same time, it's almost like it's the only type of machine this algorithm can run into, onto. Like the more you grow the number of qubits, the faster you get stuck into a plateau. Like and this is this was in a hat, like this was like, oh wow. Like so there's a paper, I'll probably share it in the channel as well later, where they show that, and they take like a really small circuit, and then they show as they increase the amount of qubits, and they keep the same or an equivalent ansatz for these, which is just like a layer of rotations, then a layer of like entanglement gates, and another layer of rotations, and just something basic. As you grow the number of qubits, the actual conversions into something that it's you just get stuck is faster. And there's then they developed a couple of ideas and techniques to avoid these, but it's still an active research area. And it was funny. I found it funny because it's like it's not that they are good for these machines, these are the only machines they are good for. And
I see. That it's cool that in this paper you're talking about is somewhat recent, or
yeah, it's actually recent, because I have it even bookmarked somewhere in Twitter. I have to search.
yeah. The what's cool is this 2013 paper, the one we're talking about.
Mm-hmm.
In that paper, they talked about how traversing these entangled they call it the non-separable state space.
Mm-hmm.
So traversing that entangled state space actually increases the number of paths that allow convergence. So what I'm hearing from you is that what we're finding is that it like if you're gonna hit a barren plateau, you're gonna hit it much quicker,
Mm-hmm.
because like as you increase qubits and you increase the entanglement, you're going to converge faster.
Yeah.
So either you're going to get to a good answer faster, or you're going to get to a barren plateau faster.
Yeah, exactly. Yeah, it's a nice way to put it. Yeah.
But I mean, that's also the power of quantum computing. In that, in our classical, we don't deal with entanglement when we are trying to converge. Classically.
Classically, exactly. It's both like entanglement is both like powerful but also dangerous in that sense.
Yeah.
Someone made a comment in one of the I'm in a Slack, like a Spanish quantum computing Spanish community. It's like, and there's a guy who actually explained that this way. He's like, yeah, entanglement is more dangerous than we think, because it just like the size of the space grows so much because of all these, that you just, he put it in a really simple words, is like you just get lost too quickly. Like there's just no, sometimes we think that the bigger the space the better, and it's not necessarily true, depending on the problem you're trying to solve. Yeah. But I think that's basically it.
Yeah.
Cool.
Kind of a side note, Scott Aronson gave a lecture yesterday.
Oh yeah, I saw you shared that, but I didn't have the time to take a look at it yet. You're talking about supremacy, right?
Yeah, and I'm just calling out one slide that he shared during that. He said that all quantum speedups, and this is powerful for me to hear from someone well respected. He said all quantum speedups come from interference.
From interference.
So it's not the superposition. It's not the fact that common way of saying that.
Give me a second. I have to go pick up. Just sorry, because someone's knocking at the door.
Go for it. Yeah.
Yeah, I'm back.
Sure.
So, sorry, what were you saying? Uh,
Oh, I was just
the interference stuff you're
saying,
saying. Yeah.
yeah. So the interference. So yeah, it's not even superposition. Well, yeah, it's that he's saying that all quantum speedups come from this interference, and assuming that the speed of the quantum computer in having this interference happens is faster than, obviously classical devices which don't have interferences. And he just broke it down pretty simply, but with um, a 2 qubit example versus
Mhm.
2 bits in a probabilistic computer. But yeah, why did I bring that up? You were talking about entanglement.
Yeah, but the about I was talking about entanglement in the sense that like that it's sort of
For the power.
it's powerful, but it's also dangerous in the sense that like just because it's there doesn't mean that that gives you directly the advantage. Um, it's and I think that's kind of why you brought it up. Yeah, I mean it's definitely interference is. I mentioned that many times, and I feel pity that like it's somewhat not like the focus on in many of the quantum computing learning materials that are available out there. Like it's maybe just mentioned in passing, but it's not like you when you focus just on the linear algebra, you actually it actually hides the interference somewhat. Like it happens within the actual matrix multiplication when things cancel out, and then you just don't see these, right? Um, and it's for me that was I think since I started with quantum computing that was the biggest eye opener when I was playing with Grover and kind of came up with this idea of looking at it from an interference perspective, and then I was like, oh, like now I understand why interference is important. That's a good example of interference. And um, because even the geometrical analogy, with the rotation of the state towards the target state and stuff, it's really neat and everything, but it doesn't really, talk about interference. It's just a geometrical interpretation of the math of the sort of the matrix transformations.
I think you have a whole Twitter thread on this, right?
Yeah, exactly. So I almost feel like talking about it again is like I don't want people to get bored of me talking about this.
Well, I mean, you're in good company, with Scott Aronson. So it was just good to have that reinforced for me. Um,
Nice.
that so when we're talking about speed ups, to look there before other things.
Yeah, nice. It's for me, I think actually it was the Future Learn course that opened my eyes a little bit, where Rod spends quite an amount of time at the beginning of the course just talking about interference, and really it's a really he doesn't go really in depth into this, but he gives a lot of examples and with sound waves and just to really illustrate the concept. And then I when I was going through this, I was like, why would there be such a why there's such a sort of an effort to explain this kind of stuff that it's also explained in a basic way. And then and I think it was there where he goes away and says, you take a qubit in the state 0, you apply a Hadamard gate, then you get into the 0 plus state, 0 plus 1 state, and then when you apply another Hadamard to that state is equivalent to applying a Hadamard to each of the components, and that's when you get interference. And I was like, oh, okay, and because otherwise, it's like I don't know, and I had never seen that before anywhere else. Yeah.
Yeah, you've mentioned this course a few times. I think I'm going to finally check it out because that's actually the only course you've taken, right?
Yeah, it's the only one, and it's not really advanced at all. It's really basic. It's a really introduction. The level is really based on the comments that I see and the stuff you guys are writing in the chat. Like when you go through different courses, it's like that's definitely far away from the level of this course. This is a really introductory course, and you go. It's the basic. Hey, this is the basics, this is some primer on like linear algebra, and then here you have some algorithms. There's some neat explanation of the QFT graphically with rotations and whatnot. And these are, industrial applications of quantum computing, and that's it. It's a simple course. It's not really technical, but surprisingly, it really at least planted a couple of the seeds that really sort of have helped me to ramp up some of the discussions and like internal questions that I ask myself sometimes about quantum computing.
Well, yeah. Do you have any closing thoughts? Or?
No, I think that's a nice way to close. To be honest, as I said, like maybe to kind of repeat again the simplicity of this paper, the VQE one. I found this probably the best reward. I think after reading this paper. Yeah.
Agreed.
Exactly. Cool. Then yeah, man. Thanks for joining. I guess we have to decide what we read next, but there were already some interesting recommendations from Diego, I think, on the channel.
Yeah,
we'll take a look. Cool.
Maybe
yeah,
we have a. Is there a poll bot or? Oh yeah, there's simple poll. Maybe someone can.
Exactly, someone can do that, and I'm thinking, I don't know, like maybe there's, maybe we should either change the schedule or just like do it more randomly instead of just planning too much for these and keeping it always on Fridays. I feel because I feel like Diego really wants to join, but like he never makes it to, I don't know. And then Gidi is also the same. He's always has stuff coming up, and then I think it would be cool to have more people in the discussion.
Yeah, and yeah, we don't need to necessarily try for every week. Maybe just once everyone can have a chance to read the paper, we just decide what we're going to read, and then
exactly.
just have a check-in. I finished reading it, and then when everyone's finally finished reading it, then maybe we just figure out a time we can all talk.
Yeah, exactly. Maybe let's do it more organically like this, like sort of not force it weekly. Because I also think that the papers we've done so far have been a good fit for like the weekly time frame. But sometimes you're like, I want to dig into this a little bit more. And maybe you actually want to, for example, if I had more time and the idea of playing with this and trying to reproduce the paper, maybe that also gives you good insights. And sometimes you want to do a bit more than just reading the paper. So I think that could give us more space for this as well. Yeah, let's do that. I like it. Cool. Perfect. Then have a nice Friday.
Next time.
Yeah. Until next time. Bye bye.